Cool, good. Right, so yeah, it's as I say, joint work with Gerhard Roehrle and Ben Martin. And yeah, it was kind of a fun project for us. So it's been conducted entirely in this strange modern world that we live in, which means I can talk to all of you all around the world. And you know, we wrote this paper entirely through Zoom, which I wouldn't have believed was possible 2 years ago. And yet, in some sense, it's pretty old-fashioned algebraic groups that I want to tell you about today. I guess, given the news that dropped into my inbox this afternoon, the sad news of Jacques Tiet's passing, that's kind of appropriate as well. I will reference at least one of his early results today. So yeah, it's kind of mathematics that wouldn't have maybe been out of place in the 1970s, but for some reason wasn't written down till this year. So yeah, let me get started. So the setup will be, I will be talking about linear algebraic groups, obviously over algebraically closed fields of arbitrary characteristic. And for the start of the talk, I want my group to be connected. I will talk a bit about the non-connected case at the end. And I'm interested in unipotent elements in algebraic groups. So let me remind you that the set of unipotent elements in G is closed. And if G is a reductive group, then that set is a finite union of conjugacy classes. And the class I'm particularly interested in this talk is the regular class in a reductive group. The class of regular unipotent elements, that's the biggest one, if you like. So that's the one of largest dimension, and it's dense in the set of all unipotent elements. Okay, and we're interested in subgroups of G, which contain such a regular unipotent element. Okay, so when you start talking about subgroup structure of algebraic groups, naturally you're led to consider Burrell subgroups. You follow the classical treatment. So let me remind you that a Burrell subgroup is a maximal connected soluble subgroup, and one reason to consider them is that every element is contained in a Burrell, in a connected algebraic group. So the main thing I need, actually, upon which all of the rest of the maths in this talk is built, is a result due to Steinberg, I think, from the 70s, that allows you to recognize regular unipotent elements by looking at how many Burrell subgroups they're contained in. So in a reductive group G, you can recognize a unipotent element being regular because it will be contained in precisely one Burrell subgroup. So this is a kind of a pretty thing, and maybe I thought it wouldn't be ridiculous to just remind you what this looks like in the sort of canonical example. So if I take the general linear group, then the finiteness of the unipotent classes, of course, is just Jordan form, and the unipotent classes are labeled by partitions of n, with the partition telling you how many Jordan blocks and what size they are. So the regular unipotent elements then, the regular unipotents are all conjugate to the standard guy, which is the single Jordan block. Okay, single n by n Jordan block. That's a regular unipotent in GLN. And then if I ask you to write down a Burrell subgroup containing this guy, well, it won't take you very long to find one. The Burrell containing U is the standard upper triangular Burrell, right? Okay, and this fact due to Steinberg is that you won't be able to find another one, and that's kind of easy piece of linear algebra in the case of the general linear group. Okay, so these are the guys I'm interested in, these regular unipotent elements. And as I say, we're looking for various subgroups containing these guys. Okay, so here is a result due to Tids and Burrell, again from the 70s. So when you start thinking about subgroup structure of reductive groups, this is kind of the starting point, really, of the industry of writing down subgroups of reductive groups that has continued for the next 50 years. So once you've written down what a Burrell subgroup is, you think about the overgroups of Burrell subgroups, you get parabolic subgroups, and this fundamental sort of structural result of Burrell and Tits says that in a reductive group, if you want to work down the lattice of connected subgroups, say, then what you need to do is think about maximal subgroups, and the maximal subgroups fall into two camps. They're either reductive groups themselves, or they are parabolic subgroups, they're maximal parabolic subgroups. Okay, this was proved by Burrell and Tits by constructing in a sort of canonical way parabolic subgroups attached to unipotent subgroups of G. So if I hand you a subgroup of G and it's got some unipotent radical, then Burrell and Tits tell you how to put that inside a parabolic. So in particular, it's not going to be maximal unless it is itself a maximal parabolic. Okay, so there's two flavors of maximal connected subgroup, the reductive ones and the parabolic ones. And from this then comes an industry of trying to write down reductive subgroups of reductive groups by working down the lattice. And that's kept a lot of people very busy for a lot of years. So I want to bring this slightly more up to date by telling you of a thing that was first written down, I think, by Serre in the 90s sometime. Not entirely sure of the order of events here. But he realized it would be useful to look at a certain class of subgroups of G, and it's kind of related to the Burrell-Tits results. I've put it on the same slide. It's the class of subgroups of G which are not contained in any proper parabolic. Okay, so this will include the maximal reductive subgroups, but maybe other subgroups as well. But in fact, you can show that such a subgroup that's not contained in any proper parabolic, then it must be reductive itself because of this Burrell-Tits result. And Serre christened these G irreducible subgroups. And the reason for that name is, again, the general linear case. So if you're staring at the general linear group as your group G, then you can recognize whether or not a subgroup is irreducible in this sense of Serre by looking at its action on the natural module. And if that is an irreducible module for H, then this subgroup is irreducible. Okay, so again, let's just record that on my piece of paper, because I will come back to this notion later. Okay, so the parabolic subgroups in GLN then are ones containing a Burrell. So the parabolics containing this Burrell that I wrote down before have this sort of block shape. So they have to contain the full set of upper triangular matrices in GLN. So all I'm allowed to do is sort of fill in little blocky bits below the diagonal, anything I like up the top and zeros underneath. Those are what all the standard parabolics containing B look like. And then in general, you see that the parabolics in GLN are stabilizers of flags of subspaces. So parabolics in GLN correspond to flag stabilizers. So in particular, the maximal parabolics are simply stabilizers of subspaces. And this is why you see this notion of irreducibility works in this case. So if I tell you I've got a subgroup that's irreducible in this sense of Serre, it's not contained in any parabolics. In particular, it's not contained in any maximal parabolics, so it doesn't stabilize any proper subspaces of the natural module. So that natural module is an irreducible module for this subgroup. Right. Hence the name. Okay, so this is the class of subgroups of interest in a reductive group. Okay, good. So I'm almost done with the sort of preliminary material. The last thing I need is a technical tool that will allow me to write down a nice, neat proof for you in about 10 minutes time. And it's how to create parabolic subgroups in a reductive group out of co-characters or one-parameter subgroups. Okay, so I'm talking about co-characters. That's homomorphisms from the multiplicative group into G. I'll denote the set of all such by Y of G. And given a co-character, I can form the set P sub lambda, which I'll sometimes write as P sub lambda of G, because there might be more than one possible G lying around. And what I do is I look at elements of G, I conjugate them by things in the image of this co-character, and then I try and take the limit as T tends to 0. And if that exists, I stick G in the set P lambda. Okay. So again, I'm going to write this down in a sec in GLN, and then you'll see that this limiting process, if you haven't seen it before, is really not complicated at all. But let me just collect some properties of these guys while I've got them on the screen. So in fact, you retrieve a parabolic subgroup. These P lambdas are parabolic. And even better than that, every parabolic has this form. Okay, so for every lambda, P lambdas are parabolic, and for every P that's parabolic, I can find a lambda. In fact, it will be several different lambdas, but I can always find at least one that gives me P equals P lambda. And various naturally occurring subgroups of P occur in quite a nice way in this formalism. So for example, the unipotent radical of the parabolic P lambda, I can recognize as the set of elements that get sent to 1, or the identity in the limit. Okay. So that's a nice, neat way to find the unipotent radical of this parabolic. And the final thing is that it also gives me a nice way to write down opposite parabolic subgroups. So what do I mean by opposite? Well, there's, as we know, there's a root system lying around here. So once I've chosen a maximal torus and a Burrell subgroup, blah, 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 I've got a set of positive roots and a set of negative roots. And my parabolic, I think of sort of sticking out in one direction. Certainly its unipotent radical sticks out in one direction. It's generated by some set of positive roots. And then I'll have an opposite parabolic sticking out in the other direction, generated by the corresponding negative roots. And then there's a Levy subgroup in the middle somehow. And that's what the notion of opposition is here. But when you work with these co-characters, it's very easy to write down opposite parabolics. So if I hand you a co-character lambda, I think of this set of co-characters with an additive structure, then the minus lambda is the one I get by just inverting everything. So minus lambda of t is lambda of t inverse, and that will give me another parabolic, and these two are opposite. Okay, and in fact, this is a good way of showing the previous 3 properties by thinking about co-characters and roots, and the pairing of co-characters and characters. Anyway, these 4 facts I will need at various points. So again, let me just quickly show you how to do this in GLN land. So a typical co-character of GLN, well, I might as well diagonalize it because its image is going to be a torus, so I can stick it in the diagonal matrices if I want. So it's going to just be lambda of t is going to be a diagonal matrix, and I'm just going to get t to various powers. Maybe I get t to the a1 up to t to the an. And these powers are integers. Okay. So this limiting process that's maybe seems a bit sort of out of place in algebraic groups land is just very easy to write down in this case. If I give you a matrix G and I conjugate G by a lambda t, then I can tell you what the ij entry of that matrix is. So I'm going to get the ij entry of the original matrix G, and I'm going to multiply by some power of t, and what happens is that the lambda t on the front gives you a t to the ai, and the lambda t inverse on the back gives you a t to the minus aj. So I get an ai minus aj in here. And then you see, if I want the limit as t tends to 0 to exist, I had better kill off all these entries when ai is less than aj, because then I get a negative power of t, and that's not going to behave nicely as t tends to 0. Okay, so the limit is going to exist as t tends to 0. It's going to exist if and only if, in fact, gij equals 0 for all I and j with ai less than aj. Okay, so then you see how I can retrieve a parabolic subgroup of the form at the top of the page from a co-character. So then if my writing's not good enough to do 4 blocks, I think I'll do 3 blocks. If I do a t to the a1 a few times, t to the a2 a few times, a t to the a3 a few times, so I've got a block, a certain number of powers a1 occurring, and then a block of a2s and a block of a3s, and I specify that a1 is bigger than a2 is bigger than a3, then I'm going to get p lambda is going to be the corresponding block-shaped parabolic subgroup. Okay, and it's very transparent how that all fits together. Okay, good. So that's all the technology I think I need for now. So let me go back to the slides and just check. Yeah, we've done this. Okay. Good. So the last thing just to say about this notion of opposition, you can see from the description of opposite parabolics and Burrell subgroups in terms of roots that a pair of opposite parabolics will generate the whole group. Okay, because the whole group's generated by the torus and the root subgroups, and that will be contained in these 2 things together. Okay. Good. Right, so I can get finally to a result. So as I said in my abstract, this is not a result that I was the first one to prove. It's a result of Testerman and Zalesski from 2013. And it sort of links together all the things I've tried to introduce in the first part of the talk. So if I hand you a reductive, well, connected reductive subgroup of a connected reductive group G, and I tell you that that subgroup H contains a regular unipotent element, then it is in fact one of these irreducible guys. Okay, so it's not contained in any proper parabolic subgroup of G. So I think this is I'm biased. I've been working on this stuff for many years, but I think it's a very pretty result, and it kind of neatly ties together quite a lot of nice stuff. I should tell you a bit about the history of this. So this was proved originally, as I say, by Testerman and Zalesski, and the proof is essentially a proof by writing down all possible examples. Okay, so you can classify within reductive groups, because reductive groups are classified. You can sort of work down, seeing which reductive groups fit inside which other reductive groups, and then you can check whether or not they contain regular unipotent elements or not. Okay, and this process was begun in 97, I think, by Saxel and Seitz, although the idea, I think, is older than that to possibly do this. And, by the time it got to 2013, Testerman and Zalesski were able to write down all possible examples of semi-simple H's inside simple G's where H contains a regular unipotent element of G. And once you've done that, you can observe then that none of them are contained in a proper parabolic G. Okay, and the reduction to simple G is straightforward. Okay, and there are plenty of examples. There are lots of examples that arise in nature, right? If I hand you a symplectic group inside a special linear group, for example, the symplectic group SP2N does contain a regular unipotent, does contain a full Jordan block. You might need to stick some -1s in instead of 1s, but still a regular unipotent. Okay, so there are pairs like that. In characteristic 0, every unipotent element in G can be put inside a little SL2. So there'll be lots of little SL2 subgroups containing regular unipotent elements, and they will all be irreducible as well. Okay, so there are lots of examples in nature, and you can classify them if you want. Okay, and then since Testerman and Zalesski wrote this down, then there've been various extensions. So Gerhard and Mahler started thinking about finite subgroups with this property. This year, Mahler and Testerman non-connected subgroups in simple G, and then plenty of other people have worked on this. But it seemed to us that such a nice sort of pretty uniform result like this should have a uniform proof. So that's what I want to show you. In fact, we were able to write down a proof that doesn't need you to know all the possible examples. Okay, and it just uses the technology that I have introduced in the first part of the talk. Okay, so let's go for it and try and write this down. Okay. So let me tell you the philosophy, the idea of the proof first, and then I'll give you in 4 little chunks, little bite-sized pieces. So the idea is to use the notion of opposition, to use opposition in reductive groups. So what do I mean by this? I'm going to be working with unipotent elements and Burrell subgroups. And the idea is that whenever I write down a Burrell subgroup and a unipotent element in it, it's kind of sticking off in one direction in my reductive group. That's giving me a positive system of roots, essentially. And so everything I do up in that half of the reductive group, I can also mirror down in the negative half of the root system. And that's something special about reductive groups. That is going to allow me to have much more control than you'd expect. Okay, so that's really the key idea, and that's why these co-characters come in useful, because they allow you to write down opposite things without having to think about it. Okay, so the first step then is to show that the notion of regular for unipotent elements passes down nicely to subgroups. So suppose U in H is a subgroup of G, reductive subgroup of G is regular in G, then I claim it's regular in H. Okay, so to see this, I'm going to use this characterization of regularity that I showed you by Steinberg. So I'm going to show that U is only contained in one Burrell subgroup of H. So suppose B containing U is a Burrell of H. Okay, well then I want to use the fact that U is regular in G, so I need to blow B up to being a Burrell of G, but that's fine. B is a connected soluble subgroup of H, so it's a connected soluble subgroup of G, so it's certainly contained in a Burrell of G. Okay, so then there exists a Burrell. Let's call it B tilde of G with B contained in B tilde, and I claim that in fact B is equal to B tilde intersect H. Just to be on the safe side, let's take the identity component of that, so I don't have to work any harder than I need to. So why is this true? Well, it's certainly true that the left-hand side is contained in the right-hand side here. Is the left-hand side is a connected subgroup of H and a connected subgroup of B tilde, but it's maximal. It's maximal amongst connected subgroups of H. So connected soluble subgroups of H, and the thing on the right is a connected soluble subgroup of H. So these two things are definitely equal. Okay, so whichever Burrell B tilde of G I choose sitting on top of B, I get this equality, but B is unique because U is regular in G, okay? But B twiddle, sorry, is unique, containing U, because U is regular. So this is the Steinberg result that I showed you at the beginning. Okay, so there was only one choice for B after all. Okay, so B is unique and U is regular in H as well. Okay, good. So we've shown that this notion of regularity for unipotent elements passes down nicely to reductive subgroups. So that's a good thing to know. So I now want to enact my plan of using this oppositeness. So we have U in B, and I'm going to write B in terms of a co-character of H. So I'm going to write B as a P lambda of H for some co-character lambda. I can do that. That's always true. H is a reductive group. So I can do that. And then I'm going to write down the opposite. So I'll call that B minus, because it's sort of sitting on the other side. And that's the parabolic of H corresponding to minus lambda. And it's an opposite to B, so it's still a Burrell subgroup. So this is another Burrell. Okay, so the two Burrell subgroups B and B minus are conjugate to each other. That's always true. Burrell subgroups are always conjugate to each other in an algebraic group. So I'm going to conjugate one to the other. Okay, so B and B minus conjugate. Say by some x. Okay, I could choose the longest word in the var group, for example. I don't really care what element I choose. I'm going to let U minus another unipotent element be the conjugate of U, and this is going to be in B minus. Okay, so I'm trying to, as I say, trying to act out what I said I would do, which is I've got U and B sticking off on one side of my reductive group H. I can find B minus on the other side, and I'm trying to find a corresponding unipotent element on the other side. That's U minus. So U minus is a conjugate of U. U is regular in G and in H. So U minus is also regular in G and in H, because it's conjugate to U. Okay, so that's inside H. I've got this sort of symmetrical picture. I've got B in the positive side and B minus in the negative side, and corresponding regular unipotent elements U and U minus. And I want to blow this up to G. Now I've got this co-character. There's a sort of obvious way to blow this up to G. So I'm going to let P be P lambda. Now the parabolic corresponding to lambda inside G rather than inside H. Okay, so this is a bigger guy in general, and P minus the opposite guy. So these are opposite parabolics in G. Now, okay, so I've got two parabolic subgroups of G now. I claim that, in fact, these are still Burrell subgroups. Okay, so I'm going to claim, oh, I just need to show that P is a Burrell G. Okay, and to see this, I'm going to show that this unipotent element U is in the unipotent radical of P, and then it will follow very quickly. So this element U is certainly in the unipotent radical of the thing I first wrote down, the Burrell subgroup of H, because all the unipotent elements in a Burrell subgroup are in the unipotent radical. So that's easy, but I've written B as P lambda inside H. So this means that if I take the limit of U when I conjugate by lambda t, and I take t to 0, remember the unipotent radical is characterized as the set of points which get sent to the identity in the limit. Okay, so in particular, U is sitting in this unipotent radical. So the limit lambda t U lambda t inverse as t tends to 0 is the identity. Now that thing I've just wrote down, that limiting thing, that doesn't see whether I'm taking the limit in G or in H. So this tells me, in fact, that U is in the unipotent radical of the big parabolic upstairs, P lambda of G. Okay. Good. So now I claim that this forces P lambda of G to be a Burrell subgroup. So why is that the case? Okay, so I pick a system of roots. And with respect to that system of roots, I can write any unipotent elements in P lambda as a product over some positive roots of some root group elements. So X alpha, say, are in the capital U alpha. These are the root groups. So when you do this, when you write down a unipotent element in terms of some system of positive roots, you can recognize whether or not it's regular. When is it going to be regular? It's going to be regular precisely when each X alpha is non-trivial for the simple roots. Okay, so I've chosen some system of roots. I'm sort of implicitly choosing a Burrell subgroup here, basically. And you recognize the unipotent element, the regular unipotent elements, they should have non-trivial contribution from each of the simple root groups. Okay, but that says this U is now lying in the unipotent radical of this parabolic. That says the unipotent radical of this parabolic sees each of the simple roots. And the only parabolics that see every simple root in their unipotent radical are the Burrell subgroups. Okay. So in fact, okay, so P lambda of G is in fact still a Burrell subgroup. Okay, so this is not a massive surprise. I started with a Burrell of H up here, right up at the top. I started with a Burrell of H. I've done some fiddling around with this lambda mumbo jumbo, and I've ended up blowing it up into Burrell of G. Okay, so in fact, the conclusion is, so this P, which is the P lambda of G, and P minus are Burrell subgroups. They're opposite Burrell subgroups of G. P is the unique Burrell containing U. P minus is the unique Burrell containing U minus. So all this is kind of forced on me just by the fact that these guys are irregular unipotent elements. Okay, so we're done now. This is a very short final step. Okay, so what am I after in the end? I'm after showing that my subgroup H is one of these irreducible subgroups. So let's try and stick it inside a parabolic. So let's suppose H is contained in a parabolic Q. Well, this parabolic contains H, so it contains U. So there is some Burrell of Q containing U. Every element of an algebraic group, a connected algebraic group, is in a Burrell. There's some Burrell of Q containing U. The Burrell of Q is a Burrell of G. So it had better be P, because P is the unique Burrell containing U. So P must be contained in Q. Well, I can do the same for U minus. And I get that P minus is containing Q. So this parabolic subgroup Q contains a pair of opposite Burrells. It has to be the whole of G. So P and P minus inside Q implies Q equals G. Okay, and that's the end of the proof, right? I was trying to show that H is not contained in any proper parabolic subgroup of G, and I've done that, right? Okay. So I don't know whether you stuck with me through that, but hopefully you'll agree that this is not a very long proof, and it doesn't use anything that's particularly complicated about reductive groups. It's really just using the fact that there's a root system lying around and this beautiful result of Steinberg that allows you to characterize regular unipotents by how many Burrell subgroups they're in. Okay, good. So just to sort of finish off with, I want to just tell you a few extensions and further results you can get using the same basic ideas. And one of the advantages of writing down a proof like this, rather than doing case checking, which has its own advantages, is that you can just adapt the proof to slightly different settings without having to do any extra work. Okay, so exactly the same proof gives the analogous result for regular nilpotent elements of the Lie algebra, and I think this is a brand new result, and it's the same statement, but instead of requiring the subgroup H to contain a regular unipotent, you require it to be, well, tangent to a regular nilpotent.
Sorry, what do you mean by tangent to a regular?
Okay, I mean if its Lie algebra contains a regular.
Okay, thank you.
Yeah. Yeah, and it's the same proof because regular nilpotents have very similar properties to regular unipotents. Okay. Maybe more interesting is that this sort of formalism that I described to you for dealing with parabolics in terms of co-characters works equally well in non-connected groups, and allows us to use essentially the same proof to write down the result on this slide, which is relaxing the conditions on H and G slightly. So now we allow H and G to be reductive groups which are possibly non-connected. So I just require that their unipotent radical should be trivial. Okay, so no connected normal unipotent subgroup. Okay, then there's a notion of regular unipotent elements inside a non-connected group. And if H contains such a thing, well, I can't quite retrieve the naive analog of this Testerman and Zalesski result because it's not true. Okay, and I'll show you a couple of examples in a second. But I can at least say that the identity component of H is G completely reducible. So this is another notion of Serre's, which, okay, it's the analog of irreducible. It is to G irreducible as the normal notion of complete reducibility is to the normal notion of irreducibility. Okay, so that's something about the identity component. And then I have to put some conditions on this identity component to avoid some pathological examples involving tori. But if H0 satisfies these conditions, then H doesn't normalize any parabolic subgroups of G0. And if in addition it meets every connected component, then it's irreducible in an extended sense of Serre's original notion. Okay, so the point of difference between 2 and 3 is that there might be proper subgroups of G whose identity component is G0, and they will be parabolic. So to get rid of those, you need to make sure that H meets every component of G. Otherwise, you get silly examples. Anyway. Okay, so this is the most general result we were able to write down in this setting. It's, as I say, you need to know what a regular unipotent is in a disconnected group. So this goes back to work of Spoltenstein from the early 80s, which I certainly didn't know about before starting on this project. So that was a nice piece of reading for me. But there is a notion. After you've written that down, everything else basically goes through in the same way. So the same basic structure of proof works. There's no need to write down any classifications. But just a reminder to me in parentheses here, these classification results are obviously very useful, so I don't want to denigrate them too much. Okay, so let me just show you a couple of examples just to explain why you need some hypotheses in this general theorem. So both of these actually still have connected G, but disconnected H. So the first of these is extracted from the paper of Mallow and Testerman I mentioned earlier. So we're working in GL4 in characteristic 2, and I take some two-dimensional torus, as that's got a sort of block shape, so it's scaling scaling the vectors, the basis vectors E1 and E2 and the E3 and E4 separately. So it's got this block shape, and then the unipotent element U is kind of swapping those spaces and acting unipotently. Okay, and you can check that this U is regular unipotent inside GL4, and also that it normalizes this torus. Okay, so I can take the subgroup H generated by U and the torus, I get some disconnected group, because U has order 4. So I get some disconnected group, this identity component is a torus, and it contains a regular unipotent element of G, but it is not irreducible in this sense of Serre, because, for example, these two subgroups both stabilize the subspace spanned by the first and the third standard basis vector. Okay, so T just scales those two vectors independently, and U swaps them. Okay, so the subgroup H will be contained inside the parabolic, the proper parabolic that's the stabilizer of this subspace. Okay, so just flicking back to the theorem, you need some condition here that rules out nasty tori in the identity component. There's sort of no escape from that. But the condition is not that H0 should not be a torus, because there are also examples where H0 is a torus and the thing is irreducible. So you have to sort of just accept that you're not going to get the most general thing you can. So in the second example, we've got another torus, again in GL4, in characteristic 2. I take the full maximal torus this time and an element representative of 4 cycle in the Weil group, and this is also unipotent and regular, but this time the subgroup is irreducible. It's not contained in any proper parabolic. That's kind of obvious. You try and find a subspace stabilized by this thing, you're going to fail, because T will be able to scale and U will be able to shuffle coordinates and you'll be able to generate everything. So this is acting irreducibly. Okay, so you need some condition. And the best we could do was this slightly nasty condition about projections of identity components to simple factors. Okay, so one final thing then, I think, before I stop, is I haven't really said anything about finite groups. So there is something we could say about finite subgroups as well within this framework, and that's this final result. So again, it's because the proof we've written down is sort of so well behaved, you can layer on some additional structure and just check that things still go through. So in this case, the extra structure is coming from a so-called Steinberg endomorphism. So that's a surjective map G to G with a finite fixed point set. So for a Frobenius, for example, would be an example if you're working over, over the algebraic closure of a prime field or something. Then if I hand you a subgroup H, which is also stabilized by this endomorphism. So sigma of H is H. And I tell you that contains a regular unipotent, then its fixed point subgroup, its finite subgroup is still irreducible. Okay, so this H sub sigma now is a finite group. So what this is telling you is if you're interested in finite subgroups of reductive groups, and you want to find nasty examples, and such examples do exist, of finite subgroups which contain regular elements but are somehow not irreducible, you're not going to find them by taking fixed points of Frobenius maps or anything like that. You're not going to be able to take algebraic subgroups and take fixed points of Frobenius maps. That's not going to work. It's going to be some sort of exceptional situation where, for example, you have a PSL to P with an indecomposable representation that doesn't come as the fixed points of a PSL over the algebraic closure. You know, some nasty stuff going on. And again, this is a new result, and it's related to some other stuff that people have investigated over the years, but it drops out from the machinery. So I thought that was a nice place to stop. So I will stop there. Thanks for your attention. Thank you.
Okay, thank you. Any comments or questions, please? Or you can use the chat also.
Do any of these results simplify in characteristic 0?
Yes. Let me think. Yeah, I think some of this stuff is much easier to prove in characteristic 0. Now let me think. I think, yeah, okay. So for a really quick proof in characteristic 0 that these things have to be irreducible, maybe I'll write it down. I mean, it is super quick. So so if I give you so if I'm in characteristic 0 and I tell you I've got a regular unipotent U inside an H inside a P, in characteristic 0, a reductive H inside a parabolic P is automatically, in fact, inside a Levy subgroup of that P, right? This is not no longer true in positive characteristic Levy. And Levy subgroups look like centralizers of tori. But a regular unipotent element isn't centralized by any non-trivial torus. So this parabolic can't be proper. Okay, it was a little bit sketchy, but I mean, this falls out very quickly because in characteristic 0, yeah, reductive groups are even better behaved than they would be in positive characteristic.
Okay, thank you. So there is a question in the chat. So let me read it. Are there some particular cases where analogous version of these results for the rational point of algebraic group holds? You mean replacing G by GK? Yes, it's my understanding.
I would think there would be, yeah, absolutely. It's something we will be thinking about.
Actually, this is close of my own questions. I mean, because you avoided buildings.
Yeah.
Today, but I mean, but it seems to me that they are present. No, I mean.
Yeah. I mean,
your argument. I mean, I think you can maybe understand them in a better way if you look in terms of of replacing parabolics by facets and
Mhm,
intersection. No.
Yeah, no, I think that's right. Probably there is a very clean argument that involves the building, and yeah, the sort of corollary to that is that such an argument might make it more transparent what worked over for rational points over a field than this does.
So we are giving you additional work. So
yeah, good. That's good. It's good to have additional work. I mean, I would guess that this sort of thing, just like it behaves well with Frobenius, would behave well with perfect fields, I would guess, right? And the problems you find with unipotent elements usually because there's some nasty imperfect extension in the way of U and the algebraic closure, right? So I would guess that things would be quite well behaved over perfect fields. But don't. This is being recorded, right? Maybe.
I stopped the recording. Okay. So
yeah.
so that's better.